Let me present you some results of our research on improving cybersecurity provisioning for industrial digital twin with augmented reality components. In general, digitization of manufacturing is a prerequisite for efficient collaboration in production clusters, and it is based on industrial data exchange within value chain. One may distinguish between different types of processing of material flows and industrial flows in such physical enterprises, and those can be represented by virtual copies, by so-called digital twins, and that is basis for smart manufacturing. Provision of robust cybersecurity framework necessitate characterization of types, variety, velocity of data, and their associated data sources. And diagram shown here illustrates architecture of the industrial data platform governed by digital twin. This industrial data platform allows also communication with external services like industrial knowledge bases, human operators. This particular interaction is provided through human machine interface, and augmented reality tools allow for improved collaboration, for timely and intuitive exchange of signals between the system governed by digital twin and the human user. And it should be stressed that some of components highlighted in red out on these data flow diagrams require specific and special attention when building the system infrastructure and also planning cybersecurity protection measures. We have identified and collected all those security threats and corresponding mitigation measures in the table presented in this slide. Actually, countermeasures are not to be invented. They are already proposed by projects like Open Web Application Security Project IoT Top 10, and for each particular vulnerabilities inherent to a component of our industrial data platform, there is also mitigation action. However, those mitigation actions, their particular implementation requires careful prioritization, as all of those mitigation actions require substantial amount of resources. So implementation of additional security controls to address the extended attack surface for this augmented reality enabled kind of digital twin, it needs some quantified assessment and prioritization of those countermeasures and these mitigation actions. And to do so, we interviewed a group of experts from cross-functional teams with more than 5 years of experience in cybersecurity and human-machine interfaces, and those experts were asked to assess potential damage to industrial 4.0 platform, to evaluate the impact of various threats, and to process their answers we have used intuitionistic linguistic variables shown in this table, and their overall evaluations distribution is shown in these and following slides. Actually, it's quite well understood as spoofing and tampering are by far the most dangerous threats. Let me remind that spoofing is claiming false identity, and tampering is malicious modification of data. Of course, we may argue that repudiation, which is denial of authorship, is so low placed in this ranking, and probably that could and will be kind of reassessed when included more estimates and evaluations from other experts. However, this shows us clearly what are preferences, what are priorities. So spoofing and tampering are clearly the most important and most dangerous threats. Here we cannot just judge based on our intuition. Here we must develop some numerical procedure. And by the way, there were also scores for information exchange, and for some components of this diagram we have reduced set of threads, and this is just reflecting character and nature of those processes, because not all of the threads are in place when we consider informational process like product specification and specification data. However, this does not allow us or anyone to neglect cybersecurity provisions for these components. Instead, mitigation measures are to be designed according to the principle of shared transposability here. So after assembled all of this data, we have implemented the procedure by TODIM method to evaluate those expert assessments, and to aggregate those assessments we have used the formula, the upper formula in this slide. Here are IJ is the evaluation of I's assessment by according to J's criterion, and those lambdas are weights prescribed to experts, and mu and nu are those fuzzy intuitionistic values. We have used this metric for calculating distance between those fuzzy numbers, and evaluated for each set of alternatives their paired dominance, and we have here both situation of advantage and disadvantage of choosing alternative according to chosen criteria. So we aggregated everything and expressed by the last formula in this slide the overall evaluation, and that calculation has allowed us to numerically assess and provide the value and position in our ranking for the most important component in data flow diagram to be prioritized when proposing and implementing security measures. But this also allows us to wisely plan and share resources when implementing comprehensive cybersecurity protections. Therefore, the method in framework of the STRIDE model allows us to quantify those evaluations by human cybersecurity expert, and we reduce possible biases which could impact decision making and support the process of secure by design development of digital twin. I should stress with our conclusions that for Industry 4.0 enterprise, which leverage digital assets and implements augmented reality tools, full awareness of the extended attack surface is prerequisite for efficient cyber defense. And here the implementation of numerical methods as TODIM methods allow us to shed more light and save lots of resources while preserving the confidentiality of the data and integrity of the digital platform. Thank you for your